Okay, welcome to Robotics 1. In today's class, we are focusing on finding velocity relations and determination of Jacobian. So today's topic is differential motion and velocities. Now, a quick recap. So consider that if you have a function f of x, so I'm going to say y is equal to f of x. This function can be plotted on x and y graph, which is something like this. This function doesn't have to be a straight line. It could be a function of a curve shape. Now, what I want to do is, I want to find out as I travel from point A to point B, as I travel from point A to point B, how much change occurs in y if x is changed. So now here is the question. The question is, how does y change when x changes by a small amount? So the key word here is a small amount, which means the x is changing by a teeny tiny amount, but we are interested in finding out the change in the y. Now, a very simple approximation here is, assume A and B over this small region of delta x. So this region is delta x. And this small region over this small region delta x, essentially this curve is approximated as a straight line. So this curve is approximated as a straight line. So this change can be easily found out as something like this. So y of b, which is the value at b, is equal to y of a plus slope of function, I'm going to say slope between AB multiplied by delta x. So this is a very simple expression. Since x is small, I'm approximating this curve by a straight line. And if I were to find out this slope, and I'm going to call this slope as s, somehow if I know the value of slope, then I can multiply that with delta x and I should be able to find out the value of b. Now same thing, if I want to go from b to c, if I want to go from c to d, if I want to go from d to e, I can use the same logic. Now here is what's happening. This equation, if I want to write it down a little bit more mathematically, I'm going to write this down as slope of AB is nothing but, slope of AB is nothing but d f of x divided by dx. So df of x multiplied by dx is nothing but delta x. Now, if you look at the problem that we have here, is my A is origin. So essentially, at point A, I'm at 0, 0. So what I'm going to do is, I'm going to go ahead and write this equation down as 0 plus dfx by dx multiplied by delta x is equal to y of b. Now, I can, if I want to be more specific, and please bear with me here, I can write this equation down in a matrix form. Is like y of b is equal to maybe df of x by dx, and then I could have delta x. And I just, for the sake of discussion, I'm gonna add zeros over here. Are you with me with this discussion? Everyone comfortable? This guy is Jacobian. What does Jacobian tell me? Jacobian tells me that if the x is changing by teeny tiny amount, then I could find out value of yb by using a differential relationship. Now what I want to do is I want to extend this to a slightly different case. So for an example, imagine that I have, and I tried to explain this example in last class, but for my own satisfaction, I just want to explain this again. So now what I have is, I have, instead of a line, what I have is I have a surface. I have a surface. And this surface is shown over here. Now clearly, in this particular case, y is function of not one variable, two variables. So you have x and z. And please note, x is an independent variable. So independent variable. And now here are two independent variables. So right now you have two independent variables. So now the question is, how do I express the same logic? So what I'm going to do is, here is what I'm going to do. I'm going to look at a teeny tiny subsection of this surface. So this is the surface. Everybody understand? This is the surface. And this is a curved surface. So I have a curved surface. What I'm going to do is, I'm going to take a small strip. Okay, I'm going to take a small strip, and then I'm going to construct a rectangle. So this is a rectangle. I just have to tell you this. This is a rectangle. And which is similar to the straight line in the previous example. This rectangle has two variations. You have a variation in delta z, and you have a change in delta x. So you have change, this is delta x. Let me show it again. This is delta x, and this is delta z. So you have variations across two dimensions. So change in y is affected by change in x and change in z. And I need to write this statement down because this statement is sort of important. So this statement is, change in x, so change in y is dependent on change in x and change in z. Now clearly, whenever you have two independent variables, you cannot use the equation of straight line, or you cannot have a direct differentiation. You can't have a direct differentiation. You need to have partial differentiation. So what I'm going to do is, and I will write this down again. So change in y is nothing but partial f divided by partial x multiplied by delta x plus partial f by partial z multiplied by delta z. So this is what it is. Everyone is clear about this variation, the notation? So delta y is partial f by partial x multiplied by delta x plus partial f divided by partial z multiplied by delta z. Now some of you may ask me, what is the significance of this? So significance of this is something like follows. Delta x is a small value. Delta z is a small value. So I'm interested in finding out the change in the y when x and z varies independently. What do I mean by independent varying? So please notice, and I will write this equation down. So this is important observation. So observation. So as y is function of two independent variables, we have to take partial derivatives. Now, what does this mean? It means, I will rewrite this equation again. Delta y is equal to partial f by partial x. And when I do this, please note, z is treated as constant, multiplied by delta x plus partial f by partial z, and here x is treated as constant multiplied by delta y. And now I would write this equation down something like in a matrix form: delta y 0 is equal to delta f by partial f by partial x, partial f by partial z, 0, 0, and here it would be delta x, delta y. Everybody with me so far? Any questions? And this is Jacobian. Now let me ask you this. There is another function, say f, which is again dependent on x and z, and I'm going to call that function y2. So in addition to, oh, delta z, correct. Yeah, this is going to be a delta z equation. So this is how it's going to look like. Now the next question is, in addition to y1, I have y2. So say I have y1 is equal to f1 x comma z. I have y2, which is f2 x comma z. I have y3, which is function of f3 x comma z. Now how do I treat delta z? Yeah, delta z in first equation, correct. This is delta z. So now if I have multiple uh, rows of different functions, I can actually append this equation something like this. So let me write just for 2. So I can say delta y1, and let's go step by step. Delta y1 is equal to partial f1 partial x partial f1 partial z, and then I have delta x and delta z. Now, if I have delta y2, I would have partial f2, because please note y2, the function associated with y2 is f2. So that's why I have f2 partial x partial f2 partial z, and I have this expression. I could go on doing that. So Jacobian doesn't have to be a square matrix. So this is important to note. Jacobian does not have to be a square matrix. So you can see that Jacobian is an extension of the first derivative. This is Jacobian. Jacobian is the extension of first derivative, and we take first derivative because our effects or our variations are small. Now, all this is great. Now, how do I use this in solving a robotics problem? And I will tell you what it means. So how do you use Jacobian? How to find Jacobian in robotics problems? So how to find Jacobian in robotics problems. So the procedure is actually very simple. The procedure is, first, set up the kinematic diagram. Solve forward kinematics. And when I say solve forward kinematics, what I mean by, you can use either DH parameters or you can use rotation matrices, but finally find out 0h1, 1h2, 2h3, and so on, and find out the positions of the end effector. Find px, py, and pz of end effector. And depending upon whether you have prismatic joints or whether you have revolute joints, just your p of x is going to be, and this is important, function, and I'm going to call this function f1. Let's assume that we have 3 revolute joints, and this is just an example. F1 is function of theta 1, theta 2, and theta 3. Assuming 3 DOF R, 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 then you are going to have PY again, but this will be F2, theta 1, theta 2, theta 3. And you will have PZ as F3, theta 1, theta 2, theta 3. And it doesn't have to be RRR. It could have a prismatic joint. So it could be theta, theta 1, D2, and theta 3. Theta 1, theta 2, and D3. So finally, you would have an expression for the displacement in X direction, displacement in Y direction, and displacement in Z direction. So Px is the displacement in X direction, Py is the displacement in Y direction, and Pz is the displacement in Z direction. Okay, before I proceed further, any questions here? Okay, now how do you form the Jacobian? Jacobian can be formed as something like delta Px, delta Py, delta Pz. Please note, Px is the function of f1. So this is going to be partial f1 by partial theta 1, partial f1 by partial theta 2, partial f2, f1 by partial theta 3, partial f2 by partial theta 1, partial f2 by partial theta 1, partial f2, this is theta 2, partial f2 by partial theta 3, partial f3 by partial theta 1, partial f2, f3 by partial theta 2, and partial f3 by partial theta 3. And you are going to have delta theta 1, delta theta 2, and delta theta 3. So now if you look at, if you multiply first row, first column, you would get the relation for Px, and I would just write this down for this problem. If you expand first row, first column, you're gonna get partial f1 by partial theta 1, delta theta 1, plus partial f1, partial theta 2, delta theta 2, plus partial f3, sorry, partial f1, partial theta 3, delta theta 3. You can perform the same multiplication for the second row, which is this guy. And then you can perform the same multiplication for the third row, and then you will get the same answer. One thing I want you to note is x1, I mean theta 1 is here, theta 1 is here. So this is theta 1. Then note, this is theta 2, theta 2, theta 2. So you have theta 2 here. And then note, you have theta 3, theta 3, theta 3. So theta 3 is here. But f1 is associated, f1 is the function associated with px, f2 is the function associated with py, and f3 is the function associated with pz. Everyone understood this? Any questions here? This is called as the Jacobian for translational motion. So Jacobian, J translation. So if you want to find out the Jacobian, this for translation, this is how you will find out the Jacobian. Now the question is, how do you find Jacobian for rotation? So now the next question is, how do we find Jacobian for rotation? Now for that, again, same process. Set up the kinematic diagram, find out the forward kinematics. But in addition to forward kinematics, I want you to find out all the rotational matrices. Find all rotational matrices. And what do I mean by rotational matrices? Just take an example. So imagine you have 0, R1. This is your first rotation matrix. Okay. Then naturally, this 0, R1 is used to find 0, H1. Then what you have is you find 1, R2. Then you find 2, R3. But and then you find out 0, R1 gets you 0, H1. 1, R2 gets you 1, H2. 2, R3 gets you 2, H3. But for Jacobian, to find Jacobian, you need to find out not only 0, R1, but 0, R2 as well. And 0, R2 is 0, R1 multiplied by 1, R2. You need to find 0, R3 as well, which is 0, R1 multiplied by 1, R2 multiplied by 2, R3. And that goes on. Even if you have a prismatic joint, if it's a prismatic joint, please note the rotation matrix for prismatic joint is identity. So I need to write this down. Rotation matrix for prismatic joint is identity. So you would use identity matrix as a rotation matrix when you are trying to find the rotation matrix for prismatic joint. Now here is what happens. To find the Jacobian, and now it becomes very simple. To find Jacobian, the overall Jacobian, which is delta theta, assume that there are 3 degrees of freedom. So 3 DOF. So R robot. So you have delta theta 1, you have delta theta 2, and you have delta theta 3. So this is going to look like 0, R 0, 0, 0, theta 1, delta theta 1, plus 0, R 1, 0, 0, delta theta 2. Because please note, our frame 0 is associated with theta 1. So frame 0 associated with theta 1. And plus you would have 0, R2, 0, 0, delta theta 3. And that is, and what you do is you combine all these expressions together and then finally write this expression as something like delta theta 1, delta theta 2, delta theta 3 is equal to a big matrix, and I'm gonna call this JR because this is the Jacobian of rotation. You can write this down as delta theta 1, delta theta 2, delta theta 3. And that is how you find the Jacobian for the rotation, and you can find the Jacobian for translation. Now, this is the gist of the chapter, I think chapter 4 from your textbook. And the next part is how do you find Jacobians for different types of robots? And let me take few examples, and that would make clear, the whole thing would be clear. So in today's class, I'm going to work out a problem by hand, and in next class, and I think next 2 classes, I would work out few problems by hand, and then I will show you how to use MATLAB so that you can find the Jacobian using symbolic computation. Many a times, symbolic computation of Jacobian is not needed. So what you could do is you can find the Jacobian numerically. Now, what is the concept behind numerical computation of Jacobian? So I want to go back to the step here. So finally, an element of Jacobian, okay, an element of the Jacobian matrix is nothing but the derivative of the function. Now, if I know the values, and this is important, if I know the values at A and B, I don't know the function. I don't know what is y is equal to f of x, but somehow, if I know the values of A and B, say A is 0, 0 and B is 1, 1, if I know the values of A and B, I could still find out the slope by equation y2 minus y1 divided by x2 minus x1. In other words, this Jacobian can be numerically integrated or numerically found out. So many a times when the trajectories are super complex, then the Jacobian, instead of getting that big, long, closed form expression, we can find out the Jacobian numerically. And this numerical Jacobian can be used to solve the problems. Okay, now what I'm going to do is I'm going to stop here for a minute, and I'm going to ask you if you have any questions. If you have any questions, you can actually type it in the chat window or raise your hand or wave, and then I will unmute you. Everyone understood what the Jacobian is? Okay, one thing that I want you to understand, alternate way of writing the same expression. I'm going to take the expression for the Jacobian. I can write the equation for the Jacobian, so, and express that in terms of time derivative. So check this out. My expression is delta px, delta py, delta pz is equal to, I have a Jacobian of translation multiplied by delta theta 1, delta theta 2, delta theta 3. Assuming it's a 3 degree of freedom robot. Why do not use 0R? Oh, yes, you are absolutely, oh, yeah, correct. You're absolutely correct, because what I said that my 0th frame is associated with theta 1. I will explain this problem in detail. Usually 0R3 would become the end effector frame, and there is okay, just for the sake of completion, I need to write this down: 0R1, 0R2, and then I would say 0R3. 3, 0, 0, delta theta 4. And I would make this very clear when I work out the problems, because the way we associate, we start with a 0th frame. So my first frame, if I have a 3 degree of freedom robot, I'm gonna have a first frame, I'm gonna have a second frame. This frame I call it 0th frame. This is my first frame. Then I have this frame, and then the last frame typically, and I want you to note this, last frame typically is on the end effector. So this is the frame on the end effector. And here I have theta 1, I have theta 2, and I have theta 3. So 1, 2. So that's why I did not consider that, because my last frame is on the end effector. That's why I did not consider this. So that's why this is not considered. And it will be clear. Let me work out a couple of problems, and then it would make perfect sense. Because since there is an end effector, if you think about it, there is no revolute joint, there is no theta here on the end effector. The last frame is on the end effector, so there is actually no theta 4 for 3 degree of freedom robot. That's why this is how it is. Okay, so if we have theta 4, yes, if we have theta 4, then what it means is you don't have 3 degree of freedom robot, but you have 4 degree of freedom robot. Does that make sense? And then you would continue what I have done over here. Any other questions? Any other questions? R00 matrix will be identity. R00 matrix is going to be identity. So this is an identity matrix. Okay, any other question? Ask away. Why are the theta values of the last component of vectors? Okay, I don't understand this question. Which vector are we talking about? Oh, 0, 0. Okay, yeah. Now here is the question. What this means is, since my rotation is about z-axis, and that's a good point. I should have told you about this. Why do I have thetas in just the last column? I mean, last row. The reason for this is, this corresponds to x-axis, this corresponds to y-axis, this corresponds to z-axis. For each frame, this corresponds to x-axis, this corresponds to y-axis, this corresponds to z-axis. And if you look at the convention that we have used, our joint variable is always about the z-axis. Since joint variable is always about the z-axis, you are gonna have this term in the last row, because this corresponds to the joint variable. So it will always be in the last row. Does that answer your question? Emma, okay. Okay, no worries. Now the last part is, imagine if you have delta px, delta py, delta pz, but I'm interested in finding out the velocities. So what I'm interested in, I'm not interested in delta, delta, delta. I'm interested in px dot, py dot, pz dot. And that is simply written as theta 1 dot, theta 2 dot, and theta 3 dot. So same thing would happen for theta 1 dot, sorry. So now I need to write this down slightly differently. Let me write this down like this. So I would have omega 1, omega 2, or omega x, omega x, omega y, omega z, which is equal to Jacobian of rotation multiplied by theta 1 dot, theta 2 dot, theta 3 dot. So omega x, omega y, omega z are the rotational velocities. And I need to explain this once again for clarity. Please note, in both the cases, the frame is the zeroth frame. Frame of reference is the base frame or zeroth frame. So which means px, py, and pz are the distances from the zeroth frame. Px dot, py dot, pz dot are the velocities with respect to zeroth frame. Omega x, omega y, and omega z are the angular velocities with respect to the zeroth frame. So these are called angular velocities, and these are translational or linear velocities. Now this needs a little discussion, and I'm gonna try to discuss this very quickly. Consider that we have a simple robot. I have a robot which is something like this. And this is my end effector. This is my end effector. Now, when I try to find out Px, Py, and Pz, now let me show you what I mean by Px, Py, Pz. If my base frame is something like this is my z. Then if this is my x, if this is my x, this becomes my y. This is my z, this is my x, this is my y. All said and done, after you solve forward kinematics, what you have is, you have the position of end effector as px, py, and pz. So this px is actually this distance. This distance is px. Py is actually the distance in y direction. So for an example, if I were to take a sort of a perpendicular, so this becomes py, and pz is nothing but this distance. So what this means, that all these dimensions, px, py, and pz, are with respect to the base coordinate system. Now that said, if you look at the first 3 by 3 matrix of the homogeneous transformation. So I need to write this down. So consider this is the 0th frame, this is the first frame, this is the second frame. So you are gonna find out 0H2, and this 0H2 is gonna look like something like this. So you are gonna have Px, Py, Pz, and you will have one here, and you are gonna have a rotational matrix which corresponds to 0, R2. And then there will be 0, 0, 0 here. This rotation matrix, when you consider the command or use the command rot to Euler, rotational matrix to Euler angles, you are gonna get theta, then you are gonna get phi, and you are gonna get psi. So theta, phi, and psi are the angles that you will get when you will use the command rot to EUL in MATLAB. And those are nothing but, this is theta, this is phi, and this is psi. So what this tells me is this end effector EE is oriented by angle theta around 0th x-axis, phi around y-axis, and psi about z-axis. Now there is one more interpretation for this, and I'll just explain it to you. What this means is, in other words, and this is super important, if I were to draw a straight line from 0 to end effector, if I draw a straight line from 0 to end effector, and clearly this straight line is not going to be in one plane. It won't be in XY plane or YZ plane. It will be a 3-dimensional vector. And I need to show this. I will show you here. How would this vector look like? This is going to look like a 3-dimensional vector. Consider that my origin is here. So this is my Z, this is my X, and this is my Y. And my end effector is somewhere over here. My end effector is somewhere over here. So I'm trying to construct a sort of a rectangle around these positions. So if I were to draw a vector from the origin 0 to end effector, if I were to draw a vector from 0 to end effector, this is how that vector is gonna look like. And the coordinates are Px, Py, and Pz. So assume a hypothetical rectangle that is enclosing the end effector position and the 0th frame. Then what happens is the coordinates of the end effector in x direction is Px, in y direction is Py, and in z direction is Pz. Everyone understood this? Now but the question is, what is the orientation of the end effector? Whether that end effector is oriented along x, along y, along z. And that orientation information is provided by the rotational matrix. That rotational matrix tells me that how that end effector is oriented. So now the additional thing here which I need to discuss, imagine instead of a point, consider a straight line. Now I know my end effector is at point X. So end effector is at point X. But point X is part of a straight line on the end effector. Point X is part of a straight line on the end effector. So now my question is, how far this straight line, which I'm gonna call AB, how far this straight line is oriented with respect to X, with respect to Y, and with respect to Z. And that is nothing but roll, pitch, and yaw. So just to give you something to visualize, imagine I have a plane here. My end effector looks like a plane. So the angle made by the plane with respect to x-axis is nothing but the pitch. So I would say my plane is pitched in this direction. This is the pitch. Then if I were to find out the angle with respect to y, that is going to be my roll. And if I were to find out the angle around z, that is going to be my yaw. And that is the interpretation of roll, pitch, and yaw. Okay, before I start solving problem, any questions? So if there are no questions, I will work out a problem. Okay, I will start with a simple problem, and then gradually we'll move on to more complex problems. So the problem is, consider the robot. Yeah, go ahead, Andrew. Do you want me to unmute you, or you can ask question via chat? Okay, raise your hand so I know where you are. Okay, here. Okay, yeah, I have unmuted you, Andrew.
There we go. Okay. I just wanted to verify the position of the end effector point is relative to the pitch, roll, and yaw around that base frame axis, not the orientation of the end effector's XYZ axis relative to the base frame's XYZ.
So what it means, and it's a good question, I need to write this down. If I were to translate X, Z, and Y, roll, pitch, and yaw are always with respect to the base frame. They are not in the body frame. So end effector body frame could be anything, but roll, pitch, and yaw will always be respect to base frame. It's also called as the inertial frame. It's also called as the zeroth frame. It is also called as the fixed frame. So end effector orientation and positions are always with respect to the zeroth frame. So that is something you should always keep in mind, not in the base frame. Any other questions? No theta and no phi. No, there will be theta and phi. So there will be theta and phi.
Sorry, I guess my confusion is the XY planes are going to be parallel, so all the rotation of the end effector is going to be about the Z.
Not really, because you have intermediate axes, intermediate rotations that would orient the end effector in different orientation. Perhaps in the robot that I have shown, there might not be rotations about X or Y, because both the degrees of freedom are about Z axis. But for a different robot, assume that the first revolute joint is perpendicular to second revolute joint, you will get a non-zero theta and phi. Does it make sense? Let me work out a problem, and that will make perfect sense. Just bear with me. Any other questions? Okay, if there are no questions, let's work out the problem. So consider the RR robot. So I'm gonna draw a very simple 2 degree of freedom robot, and gradually we'll make the robots more and more complicated. So I have this robot, and this robot is a 2 degree of freedom robot. So this is the first revolute joint. This is the second revolute joint. And what I'm going to do is I'm going to assign the coordinate systems. So this is my first coordinate system, which is Z0, X0, Y0. Then I have the second coordinate system, Z1, Y1, and then X1. And the last coordinate system is on the end effector, Y2, X2, and Z2. And please note, I have followed all the 4 rules that we talked about, and I'm going to use the rotational matrices to solve this problem. And let me give you some dimensions. This dimension is A1, and this dimension is A2. So once you find out 0R1, and by now you should be experts in finding out the rotational matrices, cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Then you need to have the projection matrix, which is x0, y0, z0, x1, y1, z1. This becomes 1, 0, 0, 0, 0, 1, 0, minus 1, 0. So your 0R1 happens to be cosine theta 1, 0, sine theta 1, sine theta 1, 0, minus cosine theta 1. Then I will just go ahead, write the homogeneous transformation, 0, 0, A1, 0, 0, 0, 1. So this is nothing but my 0, H1. Any question about the homogeneous transformation? Are we good with the homogeneous transformation? Let's do 1R2. 1R2 is again cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1. Please note, the projection matrix is nothing but an identity matrix, because the coordinate systems, they match. So I should be able to find out 1 H2 as cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0, and I will have A2 cosine theta 2, A2 sine theta 2. I will have 0 and I will have 1 over here. So this is my 0h1 and 0h2. Now I need to find out the forward kinematics. So for forward kinematics, I need to find 0h2. 0h2 is 0h1 and 1h2. You can use MATLAB, or what we can do is we can actually quickly perform the multiplication. First row, first column, second row, first column, third row, first column. And let's do that multiplication, and I get cosine theta 1, cosine theta 2, minus sine theta 2, cosine theta 2, sine theta 1, A2 cosine theta 2, cosine theta 1. Then I have sine theta 1, cosine theta 2, minus sine theta 2, sine theta 1, minus cosine theta 1. And I have A2 cosine theta 2, sine theta 1. And then I'll land up with sine theta 2, cosine theta 2, 0, A1 plus A2 sine theta 2, 0, 0, 0, 1. In case if you are wondering, this is something similar to your homework problem. But in your homework problem, if you are using the same cardboard robot, in addition to the first 2 revolute joints, you have one more revolute joint. But if you look at your cardboard robot, this is similar structure as this transformation. So now what it means is, check this out. This is my Px. So Px is equal to A2 cosine theta 2 cosine theta 1. Py is A2 cosine theta 2 sine theta 1. Pz is equal to A1 plus A2 sine theta 2. Everyone understood this? The last 3 terms of the homogeneous transformations are Px, Py, and Pz. Now what I need to do is I need to find the derivative, and I need to find out dpx divided by dt, and I'm going to call this px dot. So when I do that, a2 is constant, so a2 comes out in the parentheses. Cosine theta 2 becomes minus sine theta 2 multiplied by theta 2 dot cosine theta 1 plus cosine theta 2 minus sine cosine theta 1 sine theta 1, sorry, cosine theta 2 cosine theta 2 sine theta 1 and theta 1 dot. If I do the same thing for py dot is going to be a2 cosine becomes minus sine theta 2 dot sine theta 1 plus cosine theta 2 cosine theta 1 dot. And if I do the same thing for pz, a1 becomes 0, a2 is constant, a2 I have cosine theta 2 dot. So a2, and just so we are clear, we have to use the chain rule. So for an example, d by dt of cosine theta 2 is d by d theta 2 cosine theta 2 multiplied by d by dt of theta 2. That gives me minus sine theta 2 dot. And that's what I have here. So if you look at this expression, what I have is I have px dot, py dot, and pz dot. And I'm ready to form my Jacobian. Px dot, py dot, pz dot is equal to, now I need to collect theta 1s and theta 2s. So I would have a2 cosine theta 2 sine theta 1. Then I would have minus sine theta 2 cosine theta 1. And then for py, I will have cosine theta a2 cosine theta 2 cosine theta 1. Then I would have a2 sine theta 2 sine theta 1. And for pz, I'm gonna have 0, and I would have a2 cosine theta 2, and I would land up with theta 1 dot, theta 2 dot, and theta 3 dot. So what I have done is I have equation 1, equation 2, and equation 3. I have written equation 1, 2, and 3 in matrix form. And this guy is my Jacobian. So what I have is I have the Jacobian, and please note this Jacobian is not a square matrix because it has 3 rows and 2 columns, and that's why this Jacobian matrix is not a square matrix. But this Jacobian gives me the relationship between the velocities px dot, py dot, pz dot, and the joint angular velocities theta 1 dot, theta 2 dot, and theta, actually, yeah, it's just theta 1 and there is no theta 3. So this is theta 1 and theta 2. Yeah, theta 1 dot and theta 2 dot. Because this is 3 rows, 2 columns, 2 rows, 1 column. That gives me 3 rows, 1 column. Okay, everyone understood what I have done here? I just found out the px, py, pz, differentiated those, and then substituted them in the matrix equation. Now let's try to find out the Jacobian for angular velocities. So the next step is Jacobian for angular velocities. For angular velocities. Before we go to Jacobian, let's take a moment and look at the robot. You need an A2. Yeah. Where do you say I need an A2? Oh yeah, upper right. Oh yes. Yes, yes, yes. A2. Yeah, A2. Okay. Anything else did I miss? So once we have that, let's quickly review the robot. What we have is we have theta 1 and we have theta 2. So Jacobian for angular velocities, I'm going to write this expression down. Omega x, omega y, omega z is equal to 0 r0 and 0 0 theta 1 dot plus 0 r1, because please note that this theta 2 is about frame 1. So I have 0 0 theta 2 dot, and this expression 0 r0 is identity because the zeroth rotation of the zeroth frame. So what does this 0 r0 mean? 0 r0 rotation of zeroth frame with respect to 0, which is identity. So you have 1 0 0 0 0 0 1 0 0 0 1, and that gives me 0 0 theta 1 dot. For 0 r1, I need to look at what I have here. 0 r1 is cosine theta 1 minus sine theta 1 sine theta 1 cosine theta 1 0 0 0 0 1, and I have 0 0 theta 2 dot. So when I write this expression down, omega x, omega y, omega z, this expression becomes 0 0 theta 1 dot plus first row first column I get 0, first, so actually 0 r1, let me see, 0 r1 oh 0 r1 is I made a mistake in 0 r1. 0 r1 is 0 r1 is cosine theta 1 and cosine theta 2. So okay, so you would have 0 r1 0 sine theta 1 0 minus cosine theta 1 1 0, and when you do this you are going to have an expression 0 theta 0, this will become sine theta 1 theta 2 dot and minus cosine theta 1 theta 2 dot, and you are going to have 0 over here. So your final expression will be sine theta 1 theta 2 dot cosine theta 1 theta 2 dot, and you would have theta 1 dot. And this expression can be written in a matrix form, and then you should be able to get the answer. And with this, I'm going to stop here, but I will work out few more problems in next class, and we will look at how to solve Jacobian angular velocity problems and translational problems using MATLAB. So I'm going to stop recording. If you have any questions, I would be happy to answer.